Quisiera, por favor, que le demos la bienvenida con un fuerte aplauso al doctor Petr Musilek. Petr, welcome, Petr. Él es profesor de Ingeniería Eléctrica e Informática y decano asociado en la Facultad de Ingeniería de la Universidad de Alberta. The floor is yours. Welcome.
Good afternoon, everybody. Thank you very much for the kind introduction and for the opportunity to share some of the work which we do with this audience. In addition to being a professor, I'm also director of Alberta Power Industry Innovation Center, so it's a big consortium for industry-based research. And being at the University of Alberta, which has the largest and most prominent mining engineering program in Canada and one of the highly recognized programs worldwide, it's only natural that my expertise and my interest in energy and AI is getting also some traction with the colleagues in the mining engineering. Right, thank you. So we can imagine that somewhere in the world right now, AI is controlling power grid or routing tracks in a mine site or controlling or managing production in some manufacturing facility. But in most cases today, the operators will not understand why it made the decision or control action it did. And this gap between the capability of AI and the trust is what this presentation, this talk is going to be all about. It's not going to be technical demonstration. It's more about argument that responsible integration of artificial intelligence across mining, energy, and the digital core is not an option today. It's really something which is a big challenge for engineering for the next decade. We have to make sure that it's done responsible from the start because the consequences of doing it in any other way are too there. So with digitization, the convergence in our field of energy, mining, and data is really prominent, and it's everywhere. We hear about it at this Congress a lot, and we can see it in many places around the world. And it has huge promises, right? It can provide a lot of automation, grid efficiency, things should be cheaper, should be more green, more conscious about the environment. But at the same time, there is a big risk, right? If we use AI without thinking about the consequences and the entire settings, all the context, then we will do it unresponsibly. We would do it using a black box approach, and we won't understand the decisions it makes, and it has some large risk associated with that. They can cause real physical failures, and this is what we have always keep in mind. If we compare many applications in consumer systems, streaming devices, chatting with ChatGPT or Gemini, getting advice, those things do not have very large consequences. It can be inconvenience, people can get annoyed or frustrated, but it's nothing very serious. If we have some failures in industrial systems, and especially in safety-critical systems, such as systems in energy, mining, manufacturing, the consequences can be quite there, right? We can have safety risks. We can have environmental damage caused by, let's say, tipped-over truck. And we can have halting of production for multiple days, causing tens of millions of dollars. And it's not only the severity of those consequences, it's also their irreversibility, right? We can always reboot a streaming device, or we can easily write a new prompt because the ChatGPT didn't understand us very well. But we cannot reverse, let's say, if we have a power grid which caused widespread regional blackout. This is not something which we can easily reverse. Yeah? The damage is there. People will be affected. So, as a result, if you looked at those industrial systems, there are two non-negotiables. The first of them, there is zero tolerance for error in grids, mining, and manufacturing, because, again, because of the consequences being too there and irreversibility of those issues. Second is that the explainability, which as we will see, and we've heard about it already in the last couple of days here as well, that explainability is mandatory, not optional, right? It's really important for understanding and for other purposes as well. I'll talk about them a little bit later on. To do that, to get there, to really create a framework for applying AI and deploying it responsibly, we are proposing to consider this three-pillar system or framework for responsible AI in sustainable industrial future. And the three pillars, the three components are intelligence, equity, and infrastructure. And we will talk about each of them in turn in a little bit more detail. So let's start with the intelligence. And we will always add something more to that name of that pillar itself. So in this case, it's intelligence in context, right? We cannot take it only as something which is available, which we don't understand how it works, and it's ignorant on its own when it's making decisions and providing advice. Many systems in machine learning and AI, if you look historically, and the history is actually quite long. It's more than 50 years when people were first starting to talk about AI and machine learning. So most of those traditional systems are black box systems. They are able to learn about correlations. I have data on one side, on the other side, how is it correlated? But it doesn't help to understand or to develop and describe the causation. The cause and effect is not there. We can say it's physics blind if we are talking about mining and energy and grids. Those are all physical systems. And quite clearly, if we have something in the data, the trained AI system would consider this is the gold standard, this is the truth. But it may not be the case. Maybe the data was not collected properly, there could be some measurement errors, or just the representation of the data is somewhat skewed and biased. And the way by we can rectify the issue is to ground it physically. So instead of only relying on the historical data, in our equation is that L data, so the loss which is used to guide the training algorithm, how to set the parameters of our neural network or deep neural network or large language model. In addition to data, we can also add the physics. And again, that's something which is not new, but it's really important to follow. And it's important to do it very thoroughly and responsibly. So this L physics, the additional component of the loss, can capture Kirchhoff's laws in electrical engineering. It can capture, let's say, some laws of energy, looking at the slopes, looking at how fast a truck can move on a given slope in given environmental conditions on the road, etc. So all those things need to be considered. We have to realize what can be important, what could happen, and which physical laws should be respected, right, by the system itself. Of course, the world wouldn't forgive us if we forget to include it in our training. Something may happen just because we omitted that when we are designing the system. We can see the lambda, the value which is a multiplier, which allows the engineers to decide how strongly should this physical grounding be considered. And in our cases, in safety critical systems, which are very physical, this should be quite high, right? It should be something really very strongly playing into that training algorithm. And if we do that, we have this hybrid model, which is not only taking the machine learning laws and principles and algorithms, but also the physical grounding, the context. Then we will have AI which is causal and explainable. So we would know what to expect given the situation, what it should be. It's grounded in that physics. Not only, of course, it will be better for the purpose of being respectful of what could happen and not ignoring physical laws, but it will also make AI auditable, right? Which may be very important. In addition of not making mistakes, there are regulatory bodies which would insist on why those decisions are made, why those rules are the way they are, why the system is making specific decision. For purposes of insurance is also important. And last but not least, for the purpose of trust. And again, trust is a word which we heard a number of times here over the last couple of days, and it's very important. If operators and crews and the workers trust in the system, then it will be deployed in a very efficient way. So we can see that chain from data input. This would be the same for responsible or irresponsible system. If we add those physical laws in that second box, we will have the hybrid model processing, respecting the physical laws. Then we would have XAI interface, XAI standing for Explainable Artificial Intelligence. So not only it will be causal system, it will also be able to go back and explain why the decision was made. So if an operator wants to be able to rely on it, it's not just that the physical laws are inside that hybrid box, but can also be made very visible and explained in a language which is closed and usable by that operator. Based on this, the operator can validate the results, the recommendations, the control actions, and then execute it, right? We have an example there, let's say, description which goes beyond parameters and values is we detected grid frequency drop caused by whole track charging load. Based on this information, the operator would understand what's going on, why some things are happening, and implicitly it also contains what would be the possible courses of action, how they can decide to respond to keep the system operating properly. So that was the first pillar. Let's proceed with the second one. The second one is infrastructure awareness. And again, we can relate it to very common word in last couple of days, the digital twin, right? While the first one, the context, was about the physical laws, this is about the physical environment. It could be the map of the mine. It can be the diagram of the power network, how it looks like, how the branches, buses are connected. So it will give us the specific instantiation, where we are working, what is the environment, in addition to the laws of physics, which are valid everywhere, at least on Earth. So in this case, we can see a diagram which on left-hand side has some components of the energy grid infrastructure. We can have lines which would have certain thermal ratings. We may have some limits for transformers. We may have production and consumption of energy, let's say from photovoltaics or from wind energy. And we would typically have the digital twin, which allows us to provide that infrastructure description, right? So that's what will help us to situate it. On the right-hand side, we have similarly few inputs from the mining side of the operation. So we would have fleet and plant operations, such as payload capacity of trucks or some equipment, gradients of different components or segments of the road, and let's say the health dynamics of the equipment. Is the equipment operating properly? Is it likely that there will be some issues over the next couple of minutes, hours, or days? So there is a number of inputs, and they are then processed by the AI core. So that's the digital system equipped with AI, which will then provide recommendation and control actions after the feasibility check. So all those components, we provide some information. After the feasibility check, we will have that outcome showed at the very bottom. So we will have guarantee that all actions or recommendations will be within safe, feasible operations region. Right? So if we do this properly, we can guarantee it. And if we bring it step up, we can actually think about grid codes for AI. Grid codes for conventional grids and energy systems. They would describe what are the parameters allowed for, let's say, voltage, frequency on the grid, to keep the grid operating in the safe region. And those grid codes are important, and they are good for more traditional systems when we have large-scale generation, gas or maybe coal power plants. But if we consider systems which have a lot of renewables, distributed energy, or which are consuming energy in much more erratic and unpredictable ways, such as charging electric vehicles or trucks in our fleet. Then it may not always be the static case which works best, right? It will work in most situations, but in some situations it can be too conservative. We can stretch the system a little bit and still have safe operation, depending on the entire context. Or, on the other hand, under some situations, this can be too benevolent. Yeah? Maybe we should be more strict given all the variables around the conditions in the system. So what we would like to do is to have some dynamic, self-enforcing actions which can be described in form of rules or machine learning models, right? So this will allow us to respond more appropriately given situation. So if we embed the physics and also fairness in the autonomous decisions, then we will have operations which are safe and compliant, and they don't have to necessarily stick with a fixed set of rules, which we would start with when we are transitioning from the conventional systems to a system which is using AI. The third pillar is equity, right? And that's something which maybe some people will think, why are we talking about equity, right? This is an engineering talk. But equity is really important for building the trust, which then allows the operators, systems, and companies to run their systems efficiently, to implement them at all. If we wouldn't have that trust, then quite likely it will not be used to full potential, or maybe people would be even avoiding using that if they don't trust what's going on. The same with equity, right? Equity is about distributing in a fair way the benefits or burdens of the operations. And in mining, this is, of course, very important, quite significant, right? There is some footprint. There is something which is affecting the communities. And people have to feel that the burden is not only on them because their small town or village is close to the mine, right? It has to be distributed both ways, or they can get some benefit. So this equity is very important for the social license to operate, for buy-in, for trust, which then in turn would bring investment, right? Without the trust, it's almost impossible to scale things up. So how we can do that? We've already talked about two sets of restrictions or constraints which we can impose on our learning system. One was about the physical laws. The second one was about the environment, the map, for example, of the grid or map of the mine site. Similarly, we can come up with a set of equations and metrics which would help us to understand, to evaluate, and assess whether the system is behaving, is making decisions and recommendations in a way which is compatible with some principles of ethics and equity, whether it's fair, right? And if it's fair, then it's more likely to be accepted by workers, by the communities, by the society. In order to do that, we would typically have some input data sources. That's something which would have been collected historically over time. It will typically have some inequity. If you look back, we quite often can notice that we maybe didn't do things in the best way. We forgot about something, we didn't realize something. There were some perhaps unintended consequences, but they are encoded in the data. So if we take this data and then provide some demographic data which describe what the real situation is, this is much more sensitive data, this is why it could be typically protected, and then feed together to our AI Nexus controller, we can detect the bias. So we can see, for example, this data set which we've collected and which we are going to use to train our system is not really describing the whole context. Maybe some segments of the community were forgotten. They didn't participate, they didn't complain because they were losing power, and therefore, this is not now included in the data. So we can detect it, and then we can mitigate it. If we are aware of it, then we can make some actions, make some adjustments to have a better way of reflecting this equity. We can then decide for what we need to optimize, and we will end up with fair distribution of outcomes, both, as I said, benefits and possibly burdens as well. The community can share on the benefits, and there will be much better buy-in. So in the end, through this equity-aware policy engine, so physics, infrastructure, and now equity, we will get to a system operation which is just and sustainable as a consequence as well. So let's have a look at a simple case study. We are talking about energy mining nexus. So here we have a situation when on the left-hand side, we have the mining components and inputs. We have the fleet data, we have the load demand from, let's say, processing plant or from charging station for our EV fleet of trucks. We have production schedule for the mining. On the right-hand side, we have renewable generation, energy storage, and we can monitor the capacity of storage at any given time. And we have some indices of grid stability. So just on its own, we can see that this is really something which cannot be controlled, comprehended by a human operator. It's too many variables to really do optimization. That's why I'm talking about the nexus, right? It's really much more complex than the individual components or their sum. So this controller can then provide a lot of benefits if it's based on AI, if it has computational power to really do the optimization right, to take into account all, in this case 6, but it could be more, types of variables, we can expect it quite good outcomes. Typically, we would have 10 to 20% improvements in energy cost reduction. We can get up to 30% in carbon reduction if we are using renewable energy, and if we schedule the charging and the operations right, so it's in sync and we are not wasting the energy, perhaps thanks to having the storage capacity available as well. And we can also expect improvement in the life of the equipment, right? If we do the maintenance right, then we can use it longer to our benefit. So this is something which is certainly worth it. But there are risks that some things will not be right based on the data which we are using. So let's have a look at the two smaller examples in separation. The first one is related specifically to energy, and this is an example from energy management, let's say in a city, right? We would have data which has been collected over the decades, and quite likely it will be biased. We have it illustrated there. Maybe there is an affluent neighborhood which always has the power available. There are poor neighborhoods where people just got used to it, that sometimes they will lose the power and they are not complaining. And therefore, all the data will have this encoded in it, right? So the risk, if we use this data to train our machine learning system and then to operate the grid, is that we will just amplify this. This energy poverty, let's say, in making access to grid and bill savings, will not be available to low-income people from those other neighborhoods. So if we develop some model which is fairness-aware by putting together metrics to evaluate if it's equally distributed, both in terms of access and availability to get savings on bills, etc., then we can develop a system which will provide reliable service and grid resilience for everybody in those communities. On the mining side, an example could be workforce and resource allocation. Right? We may decide AI is powerful, it can help us to decide who should do what on our mine side. And again, looking historically, quite often, there would be mistakes made, unintentional consequences, and the data describing historically how the hiring has been handled can contain this bias, right? So we can have legacy disparities, which will be funneling underrepresented groups into labor-intensive roles. This, of course, is a risk that it will create automated glass ceiling, right? We will have a hiring system which will be sending the same groups of people to the shovel, right, to do the labor-intensive works, and they wouldn't have chance, or they can be educated, they can be capable, they wouldn't have much chance using the system to get to better positions. So again, the solution would be to develop fairness-aware model by encoding those biases or safeguards to avoid them. And therefore, we will have equitable access to high-value and safety-critical roles for all qualified workers. It's important to realize this is not just about justice, right? It's also about not wasting talent. If you do it that way, there could be highly qualified people who would never get the chance. So we want to avoid that as well. So I described that the triangle, those three pillars of responsible AI, let's have a look where we can operate it. We've heard a lot about clouds, and we also heard already today about the edge, right? So this is very important, not only for the technical perspective, but also for some alternatives as well. The edge would be very suitable for the types of computations and decisions to be made and control, which needs to be made on site, needs to be made fast, and perhaps needs to be made with the data which we don't want to share with a cloud operator somewhere else in the world. So this will be best for critical, time-sensitive operations at the source with the added benefit of having the full control of the data, not sharing with third parties. But it's not going to be good for all what we need. Sometimes we may need to retrain a model. We may need to do more larger scale analysis, and the computing power which we have on site is not sufficient, and it wouldn't be economical to bring a supercomputer, right? And to just invest to this type of infrastructure locally. Then we can shift it to the cloud. Of course, the disadvantage would be relatively high latency. The decisions may take seconds, minutes, sometimes even longer. But it can provide us with a lot of benefits in form of advanced analytics, machine learning training, etc. It's almost always a hybrid approach. It's not one or the other. It's some combination, and how much will be at each level would differ from case to case. We've already mentioned that we can use AI to help us with supporting decisions, providing scenarios. So let's have a look a little bit more detail how this could actually work. In conventional cases depicted on the left, we can see that that operator is quite likely facing information overload. There is too many panels, too many graphs, too many variables which they would have to follow in order to control the system, to make the decisions on their own. There is still a lot of automation. We are measuring, we are processing the data, we are displaying dashboards and graphs, but still the decisions are fully in the hands and in the brains of the operator. So the data has to be interpreted manually. The response to anomalies, some issues, will be relatively slow, and there will be very limited capacity for considering and analyzing different scenarios. What should I do? Or if I do A, what will happen? What will be the outcome? So if we use AI in a proper way, then it can provide us with real-time insight. It can sit on the data streams, monitor them, and see what's going on, provide recommendations. It can analyze, generate and analyze number of scenarios. So we can look what could happen, what would be the outcome of a decision A, B, or C. And therefore, the cognitive load would be much reduced, and we will have much more informed decisions made much faster, and therefore the operational resilience of the entire system, where this operator is a critical component of as a human, will be much improved. So using the generative AI as operational copilot is the right way to go. Of course, still considering and respecting all the constraints which we've mentioned so far. I'm going to probably just skip this slide. Just one important distinction. We were talking about cyber-physical resilience or cyber crime here in the past. And we heard about examples of extortion, somebody asking money for data. What's really important to note and to realize that if we have an IT system controlling physical operations, then cyber resilience becomes physical resilience, right? If there are issues with the security and safety of the IT part of the operations, it can materialize, it can cause accidents, it can hurt people, it can cause damage. Another aspect of this, and we've concentrated today in this talk and in many others on that human in the loop supporting the decision making. We just covered that 2 slides back. But there are other ways where we can see clear benefits of applying AI in this type of operations. We can have augmented intelligence, not really replacing people, but providing them with much better tools. They can have manuals and documentation at their fingertips. They can have enhanced visualization of the status of an apparatus, such as the transformer here. So the AI is not really replacing the human. It's not a robot, right, which is crossed. It's a handshake. It's something which is really very much supportive. The third example on the right is about upskilling and workforce transition. And we had a good conversation this morning during breakfast with Peter about this being a repeating theme, right? Things are, when something new comes, it doesn't mean that people will lose work. Maybe that specific job will disappear. There will be probably many more which will be newly created, which will be necessary. Different type of jobs, but it's not really just crossing the hiring position. It's creating new ones as well. In order to get there, we need to adopt some structured approach, and we are suggesting to have this 3-phase approach. The first one, which would typically take between 1 and 1.5 years, is standardization of data and governance. This is something which is like the planning stage, right? Nothing really happens. We are not going to save any money, but if we skip it, then the second and third phase will most likely not end up very well. So data fusion, interoperability between, let's say, mining, energy, and digital operations, security protocols, and guidelines, how AI should be in operation of a company used in an ethical way. If we are done with this, then we can proceed with the second phase, which is hybrid modeling involving machine learning and physics. So those will be pilots. And here is an opportunity to already get some decent return on investment. There are some low-hanging fruits, such as energy management or predictive analytics and maintenance, right? We would deploy digital twins, and we have a good opportunity to already start getting a lot of benefits in terms of savings and productivity of our plants. And finally, based on this experience and typically working together, this is not something which a single company can do together, so that will be great opportunity for collaboration, right, between multiple mining operations, companies, countries. How we can put this experience together, how we can develop frameworks which would be useful for our industry in terms of application of AI. So what I would like to close today is first expressing the hope that the paradox I mentioned at the beginning, when if we are increasing the intelligence, we are somewhat losing control, right? If we do it in the proper way, and if we consider the 3 pillars of intelligence, infrastructure, and equity, then we are regaining that control, right? The responsible AI, which is physics-informed, infrastructure-aware, and designed for equity, doesn't really sacrifice capability for safety. It syncs them together, and we can get both. I would like to have those 3 closing arguments. First, engineering trust is as important as efficiency. It's not something additional. It's really very important. If we don't have system which people can trust, they won't use it, as I mentioned before. So we have wasted money, right? We can have the most expensive AI model. If people don't see it as something they can trust, they can rely on, they won't use it, or you would use it in the wrong way. So engineering deliverable could also be considered for trust. It's not just the efficiency, it's not just the technical system, but it's also how the system works with people. The second one is that we are now at the stage when all those tools are available, right? We don't have to have research to develop them. They already exist in a certain way. So it's more about the willingness of organizations to use them, and to use them with all the safeguards, which I mentioned, right? And finally, we need to realize, and it's a very good thing to realize, that trust enables scale. It's not only about buy-in, but if people trust communities, workers, investors, operators, then it's much easier to convince investors to get more infrastructure, make things bigger. We can collect more data, we can amplify the intelligence. So it's really a full circle. So to engineer the future, engineers should build AI they can trust, and then the system, the world can trust with that AI. Thank you for your attention. This is all what I have for today.
Thank you, Dr. Petr. Thank you so much. We have a present for you for this outstanding presentation. Thank you again for being with us today, for visiting us. Come again. Great.